You may be wondering why there's a picture of beer. Well, quite simply, that's the history of the t-test, actually, is beer. More specifically, I think it was a stout that they were working with, but basically the idea was there was a simple way to test for quality. You could compare one vat of beer to another and make simple comparisons, and that way you could generalize to the entire batches, so to speak. And that statistic was developed, quite a long time ago, and it's still in use today. In fact, it's one of the most common statistics that are used in psychology. It's a very simple, very straightforward, easy to understand, and it gets used. And in some senses, it gets overly used. So we'll look at it in some detail. I'm not going to go into all the formulas and things like that. Your book covers quite a bit of those, and it does a pretty good job. So. But interpreting it is something that I want you to understand, and I want you to understand what goes into it. So let's look at the whole thing and go from here. First off, we want to look at what's called an independent samples t-test. And this is the most common one that we're going to run into. Typically, it's used to detect differences between the means of two independent groups. So what does independent mean? Independent simply means that the groups are not related to each other, right? So it's not the same people, and they're not influencing each other in some way. So the groups have to be separate. There are a couple of assumptions that are required for this statistic to be used. The first one is that your data is normally distributed. If your data is not normally distributed, fast forward to the end of this lecture series, and you will then learn what to do. But that's one of the assumptions to use the t-test. The other one is that your variances are the same across both groups. And so the group 1 and group 2 have a similar variance, and you can test for that. And there's another statistic out there called a Levene's test, which tests for the homogeneity of variance. But the point is that if your variance is not the same, then the statistic is no longer valid, and if your data is not normally distributed, then the statistic is no longer valid. Now, the issue with assumptions is that you have to test for them separately, and when you're reading journal articles, you better find a statement in there that says we tested for our assumptions and we met them, or something like that. Because if they don't have that, then you don't know if they tested for them. And a lot of people that don't know much about stats think that you can just use the software and off you go and it gives you a result. Well, they're half right. The part that they're right on is that sure, you can violate normal distributions and violate homogeneity variance, and guess what? SPSS or whatever software tool you're using will spit out an answer for you. It's just that that answer means nothing because you violated the basic assumption of the test. So people that don't run those tests for their assumptions are misusing statistics. And in some of my other stats classes, I really go off on that, and it's really a big pet peeve of mine, and you'll see that in the literature. It's very prominent in school psych that people don't actually test for their assumptions, so you have to watch out for that. Although the more I read and the more current journal articles, they're getting better. It's just that it's not at the level that we'd like it to be at yet. So there's a lot of misuse and misrepresentation of numbers and things like that. So you have to be cautious. If they didn't check for the assumptions, then you just want to be a little bit more skeptical about the results that they're presenting. So let's look at the statistic itself. This is one of the most easy statistics there are. Right? It still follows that same between groups variance divided by within groups variance thing, so let's look at it. So right there, the numerator, difference between the means, denominator is the estimate of the error. Remember what standard error was, and we think about error in terms of the inaccuracy of your measures and things like that. So that's the within groups variance. Right? So again, variance is the component to all this. You need variation in order for this to happen, because if there's no difference between your groups, then the numerator is going to be extremely small, or 0, and 0 divided by anything is always going to be 0, so your final result for your statistic is going to be basically 0, and I guarantee you that's not a critical value. And critical values, keep in mind, I'm not sure how well your book goes over them, but it probably has a bit. Critical values are that level at which your statistic, your output, is significant. It's what I've talked about in the past, where you look up that statistic on a table, depending on the sample size and some other things, and then you can find out what the critical value of t is. In other words, if your t-score as the result of this formula here is bigger than the critical value, then you end up with significance. So that's kind of how all this thing works. So let's look at a couple of the components here. There's one thing that we really haven't talked about that we need to, which is degrees of freedom. Degrees of freedom is kind of a bugger. Right? It's like, well, what do you mean degrees of freedom? Well, it has to do with how many numbers are free to vary in order to get the result that that you currently have, and that's kind of odd to say, but think of a set of numbers like 2, 3, 4, 5, and 6, and if you calculate the mean of 2, 3, 4, 5, and 6, you get a, what's the mean there? I think the mean is, let's see, 2 and 3 is 5, and 5 is 10, and 10 more is 20 divided by 5, so the mean is 4, right? So if we take away any one of those numbers, right? So let's go 2, 3, 4, 5, 6 is our number. Now let's set our mean at 4, right? Because that's what we got from our sample. Now let's assume that's going on at the population, and we're generalizing this to the population. Then we're going to take away one of those numbers, right? Because we already know what the mean is. We know that's 4. So now we're going to take one of those numbers away. Let's say we're going to take away the 4, right? Or for argument's sake, let's take away the 3. So now we have 2, 4, 5, and 6, and we have one empty box left over. And the idea then is that you know what number has to go in there, right? So there is no room for that score to vary. So we're going to, in order to make that mean of 4 using the rest of that sample, that thing is going to have to be a 3. That box, that empty box, is going to have to be a 3. Let's look at it in a little bit different way, and then I'll come back to that example in a second. I kind of got ahead of myself. All right. Degrees of freedom is about your ability the ability to have choices. Right? How many scores are free to vary? So, for example, if there's 15 positions, playable positions on a rugby team, so the first player, you have 15 choices to assign them to, right? So if we just got a group of 15 folks, we could say, all right, you're going to play the halfback or the fullback or whatever, right? So you're going to play that particular position. You have 15 choices of where you can put that first person. The second player, you have 14 choices. Then so on and so forth until you get to that last player. When that 14th player, or when that 15th player arrives, you have only one slot and you have no freedom of where to assign them. So degrees of freedom is simply calculated as the total sample size minus 1. So with our 15 positions on a rugby team, there's a typo on my slide there. It should say the 15th player arrives. You only have one slot left, and there's no freedom of where to assign them. So the degrees of freedom you have is really always your n minus 1. And let's talk a little bit more about that here. That has to do with, like I've said earlier, that the number of observations that are free to vary at the population level, because we were establishing this stuff at the sample level, right, in our study, but then we're going to generalize it to the population. So we need to talk about, we need to make some adjustments for that, and this degrees of freedom thing is one of those ways to make adjustments. All right, here's some more detail on it. So if we take a sample of 15 observations from the population, they're free to vary in any way, any number, etc., and we use that sample to create an estimate of the population mean. Okay, you're with me so far, pretty straightforward. All right. Now we're going to hold that constant, the population mean. Of course, in reality, it's just a sample mean because we just sampled something, but we're going to assume it's a population parameter, so we're going to call it a population mean. All right. Now, to keep that mean the same, all right, at the to assume for the rest of the world, right, or the rest of the population that you're interested in, we can't vary it. So the mean stays the same, and only the other scores are able to vary. So 14 scores can vary, and 1 is the mean, right? And the idea is that that last number that fills that data set to get you to the known mean, right? That one is forced. If you already know the mean, you've got 15 slots to put numbers in. When you get to the last one, the number is simply a mathematical calculation. It's not free to vary, right? Because you have to be able to get it back down to that whatever mean that is. That's why the example that I was talking about earlier with regard to the data set of 2, 3, 4, 5, and 6, if you drop that 3 and you run it and you say, okay, in order to make that mean of 4, what's that last data point have to be? Well, it has to be a 3. It can't be anything else. Right? So, and it would be, if your mean was set at 5, for the population parameter, then you would have a different number. It wouldn't be a 3 to fill in there. It would be something else, right? So it would be a 3.12 or something like that. So it would be forced. So you don't have a choice there. There's no freedom. Okay? So we understand that how that works. And the easy way to think about degrees of freedom is just that it's your sample. It's a group minus 1. And we're going to look at how that applies, because sometimes there's sometimes your overall degrees of freedom is n minus 2, but it relates to groups, and we'll talk about that here in a second. And really where it becomes important is that when we look up critical values for t-tests, it's all based on degrees of freedom. Okay? and so in other words, sample size. So degrees of freedom is directly related to sample size. Degrees of freedom allows us to interpret or find out where our critical value for our t-test or our ANOVA, whatever it is going to be, and as a result, we would then decide if the statistic is significant or not. So it does play a role there. There's some other utility of it, and we'll look at that here in a couple of minutes when we get to that point. So the example here is kind of how the degrees of freedom happens in a t-test. So in a t-test we have two samples, right? So and we have those independent samples. So we have two different means because we're going to compare those means. And so we have n-1 for each group, right? So for the group for 1, it's n-1 is our degrees of freedom for that group. For group number 2, it's n-1 for that group. So in reality what we have is our total n-2. Okay? So that's how degrees of freedom for t-tests are really easy, and you'll see at the end of this slide set where that comes into play and how it's reported in the literature, and it's good to know what that is, and it helps you understand a little bit about the statistic. Right. So let's look at within groups designs. So we've talked about our t-tests for independent samples. So let's look at t-tests for related samples here. Right? So within groups designs are really straightforward. It's the same people, and it's typically called repeated measures. We're going to compare people to themselves because they're their own best control. And the easy way to think of a repeated measures design is that every person is going to receive all levels of the independent variable, both a control and an experimental condition in a t-test. In t-tests, we're only going to be comparing two means at once. That's all we can do. We can't compare 3 or 4 or 5. We can just compare 2. Doesn't matter if it's independent or within groups. So now what we have is a different type of t-test because it's definitely not independent. So we have to have an adjustment to our statistic a little bit. So we're going to use a t-test for related samples. Right? So we're going to use that related samples t-test, right? And we can compare how people change over time. Right? And usually we're looking at how people change after some independent variable gets presented to them. Okay? So related samples research allows us to minimize error variance. And how does it do that? Well, that's because the same amount of variance from time 1 is going to be present in time 2, because remember the error variance, because what we're talking about there is the difference between individuals within each unit, right? So within each within each group, and you already have it for the first group. You establish it for the first group. In the second group, it is the same number of people. There's not just the number of people, but it's the same people, right? So those differences between each other are going to stay about the same. As a result, you end up with a much smaller denominator in your statistic. And when you end up with that smaller denominator, it makes things easier to detect differences, but you have to account for the fact that those scores might be related to each other. So there's some small groups. There's some small adjustments that are made in the statistic, but we don't really need to go into all those little small adjustments. But the basic idea is that it's a completely different procedure, but it does the same type of thing. We got time 1 and time 2 rather than group 1 and group 2. So we're going to measure people at time 1, compare them to time 2. Oftentimes there's an independent variable that happens in between there. Again, it minimizes error variance, so it becomes very sensitive and allows us to detect differences very easily. Okay? And this last point here is just talking about what I just said a moment ago in a slightly different way. So those differences that exist within those groups, they're the same. So we know that. So we're making our overall variance for that denominator or within groups variance is actually going to decrease overall. So it just makes it a little bit easier and allows us to control for certain threats to validity. So let's look at an example of repeated measures. Right? We got group A, they're all smokers, right? So you want to give them a chance to benefit from the experiment, so you intervene with all of them. Okay? So we're not going to do a random assignment to conditions. We're going to put everybody through the same thing. So we're going to compare the amount of smoking from week 1 to week 10, get an average of all people on the 2 measures, week 1 and week 10. That's your 2 measures. Right? And then we're going to compare those means. And that's all there is to this. Okay, we're going to take the average from week 1 and compare it to the average to week 2. And then we can run a t-test between those 2 times, as long as we're using a repeated measures t-test. And it will tell us whether or not there was a significant difference between those groups, or between those times, from time 1 to time 2. Right. Let's look at interpreting it, because that's what I've been just trying to get at here really quick. The first one is a t statistic, and this is often how it's reported in the literature. So t with a 24 in parentheses equals 1.73 comma p greater than 0.0 or less than 0.05. What in the world, right? In reality, you don't read this like I just read it. You read it in a slightly different way. Okay? let me see if I can read the sentence for you. All right, so here, this functionally reads as a sentence, and here we go. The t-test equals 1.73 with 24 degrees of freedom and is significant at the 0.05 level. Another way to read this: a t with 24 degrees of freedom equals 1.73, and it's less than the p-value of 0.05. Just another way to read the same thing. So the parentheses is your degrees of freedom. So t with 24 degrees of freedom, right? That tells us that there's 26 subjects in the study, right? Overall. So now you know that there's 13 people in each group. Okay? And sorry about my phone going off there. It's really going off. All sorts of messages coming in. And then let's see. The second one, and we're significant. We set our p-value at 0.05, so we're significant in that particular case. So we have a significant statistic. That means that 1.73, that's the result of the t, that's the result of our our formula of the between groups differences divided by the within groups differences, right? And we end up, it must have been bigger than the critical value that was determined based on sample size, in other words, degrees of freedom, and our p-value. And our p-value of 0.05, so we have a smaller probability, we have a lower than 5% chance of getting that number given all those criteria. So it is significant. Right? The second one is not significant. T with 4 degrees of freedom equals the 2.0, it's not significant. So you have to realize that just because the t statistic is bigger doesn't necessarily mean it's going to be significant. It depends on all those other factors like degrees of freedom and the p-value that you've chosen. Okay, now that we've seen how that's interpreted, and that's pretty much it for t-tests. But I do want to show you that there's some alternatives here, and the alternatives are non-parametric tests. So when you violate your assumption of normalcy, you should just say, you know what, I'm done. I need to use something else. I can't use a t-test now. So go into a different category, and it's really straightforward. We've got a couple of different non-parametrics that we can use. So let's go through them really quick. All right? They're used in place of the parametric statistics. Again, the parametric just means normal distribution, so the statistic that requires a normal distribution. So if the t-test is there, if your data does not have normal distribution, then you're automatically going to use a non-parametric. Right? There are specific procedures that we use in order to make sure that normalcy is not one of those assumptions. It's really straightforward, and we're going to look at it here in a second. Right? In other words, we're not going to use the mean. We're simply going to create rankings of the raw scores, then analyze those rankings, and look at how ranks change across groups and things like that. Okay? So let's look a little further wherever this darn thing keeps getting stuck on me. There's my phone again. It's hilarious. I'm popular today. This is rare. All right, independent samples, right? Again, for every scenario that we have for a t-test, then like the independent and related samples, we have an equivalent in the non-parametric world, right? So we're going to compare two groups of independent samples. It's equivalent to the t-test. It's called the Mann-Whitney, or there's another one, and it's called the Wilcoxon rank sum. Right? So the Mann-Whitney test and the Wilcoxon rank sum, and then we're going to look at how that logic is done here. Right? So we're going to ignore groups. We're going to take all of our data points and we're going to rank them from lowest to highest. First place is your lowest number, second place is in the second place, and so on and so forth. And we just put those all in order, and we give each data point a rank. Is this first place or second place? And the idea then is that if the groups are the same, you should expect a similar distribution of ranks in each group. So group number 1 and group number 2, they should both have similar ranks overall, right? Because you're ignoring those ranks, or ignoring the groups ahead of time, and I'm ranking all the data. So if they're the same groups, then it'll bounce back and forth. You'll have some 1s in the first group, and some 2s in the first group, and some 1s and 2s in the second group, and so on and so forth. You'll have some low ranks and some high ranks in both groups at about equal rates. That's the idea, that's the logic, right? So then we can sum these ranks, right? And they'll likely be similar or no difference. They'll likely be similar. In other words, there's no difference between the groups. If those differences if those sums of those ranks are not different from each other, then we're basically going to say that there's no difference between groups. Probably should have had this a second earlier, but the idea is that when we do these rankings, you're going to get rankings that are tied. You're going to get scores that are the same scores, and we deal with that really easily by taking the ranks that all those scores would have had and average the rank, and then they all get those things. So those raw scores get if we have ties, then the same raw scores get an average of those ranks that they would have. So if you had 3 2s, you have let's say we have our raw data as a 1, 2, 3, and a 4, right? And then our ranks would be really straightforward, 1, 2, 3, and 4. But maybe our raw data is 1, 2, 2, and 4. So now we have something odd. It's like, how do we deal with that, right? So our ranks can't be 1, 2, 2, 4. It doesn't make sense to rank it that way because you still have 4 places that you need to rank. So you have 1 for the low score, and then you have these 2 2s that you got to deal with. So you can average those ranks together. They would have been 2 and 3 ranks respectively, or they take the 2, the second and third place in terms of ranks, even though they're the same number. So we're going to average those and go, it's 2.5. So now you have your ranks are 1, 2.5, 2.5, and 4. Basically, it works like golf, if you want to think of it like that. And again, if our groups are different, then there will be a disproportionate amount of high ranks or low ranks in one group as compared to the other. The other option that we have here is what's called, for non-parametric, is 2 related conditions. It's a Wilcoxon signed rank test used when the data is related. In other words, repeated measures, same type of thing. Same as the dependent samples t-test. We're going to calculate the difference from time 1 to time 2. All right? So we're going to take all those scores for each person and go, okay, how much did they change from time 1 to time 2? So we're really looking at as change scores here. And then we're going to make a note of whether that is positive or negative. We're going to drop all the people that did not change at all. Then we're going to rank those differences. Right? Sum the positive ranks and sum the negative ranks. And the actual stat is the smaller of those 2 values. It's really that simple. Non-parametrics are really cool. They're very intuitive, and they're very, for a statistic, they're elegant. Right? They're really simple. It makes a lot of sense. I really like non-parametric statistics because so much of our data in psychology is not normally distributed that I think they're underused and completely underappreciated. But look at how simple that is. It's just, there's no guesswork going on. It's like, let's just look at ranks. How much do people change? And we go from there. And there's a lot more to it than this. We're just kind of scratching the surface in terms of how do you get significance and how do you estimate this stuff at the population level and all those things. And I'm not going to go into it. Your book doesn't go into it. It's way beyond the scope of this course. But know that there's a bit more to it. But in it, there's some really elegant stuff and almost sexy number stuff going on in there when it comes to playing with ranks and things like that. And it's really cool. I really enjoyed doing this work in the past. So that's about it for this stuff. Hop on and ask a question if you need any other assistance. See you soon.